The singularity itself went through many stages here. First, you have the Planck epoch, static cloud of neutrinos and electrons. It's this. Now, technically, all this energy is really buoyant. This is where the flatness comes in. When it starts to get denser, that's when the gravity starts to take hold. At its densest, it warps space. Similar to this. Of course, it's a lot heavier and denser than the planet is, so this is going to be warped a lot deeper, you might say. So it starts out at a near flat line, but then it starts to collapse. And this is why buoyancy and density coincide with each other, and gravity, because you have a spatial value here. This buoyant, that means it covers a large area. But the spatial value decreases between the particles, and it gets dense and heavy. So prior to the singularity, it's losing entropy and gaining speed to collapse. Once it collapses at its densest point, the singularity here, it's going to end up having spatial value increase. You might say inflation. So this is where buoyancy, density, and static all coincide with each other, along with gravity, because they all tie together right here. So it's high gamma radiation, absolute zero, 459.73. Now there's no color here, but it's at 459, then 455, 452. It's starting to build color. And you have muon catalyzed fusion going on. Or you could say cold fusion. As this color charge builds, you're going to get the tau. Now the tau can decay into hadrons, meaning it has enough color charge and mass to be able to do that. And this is a type of induction. So you have an inversion wave here. You have the high gamma, high energy that's going to start evening out to a more mediocre energy phase. And it's losing entropy, meaning the wave is getting stronger. So you have two waves here that are inverted from each other. And this is one reason we have the inverse square law. Once the singularity forms, this is white light, blue and white, because blue and white are the hottest. Now, as the singularity, it's a neutron star. It's the densest nucleonic quark-gluon plasma. But at this point, it's heating up. Once it reaches this apex, it's going to start cooling. And a neutron star cools no different than any other star. But it goes through a different type of process. As it inflates, the nucleons are going to be released, and you're going to have protons and electrons and light. As this is happening, eventually H6, you're going to need H5, H4, then tritium, then deuterium, then protium at its coolest. And then it's going to boom, die. Then all that protium, or those atoms, are going to be emitted, and then stars are going to form from hydrogen or protium. This is why there's less tritium, a little more deuterium, and then the most protium. Because these were 3, 2, 1, boom. So the neutron star cools and inflates into a gigantic atom, which is basically a protium star. That's the singularity at its coolest. When it's its quark-gluon plasma, it's trying to decay and inflate. As it's inflating, the quarks are decaying, and they're going to stabilize into up and down quarks, which is going to help build nucleons. So all this energetic gas with all this floating buoyancy is going to start condensing, because that's exactly what water does, because we live in a plasmatic universe. And when it becomes a cold Bose-Einstein liquid, it starts to heat up. It becomes a plasmatic gas, which is the quark-gluon plasma, or the singularity itself. Once that plasma goes into its big bang or inflates into the universe, it's going to become small bits of plasma, which are stars, and bits of hail, which is basically the solid matter in the universe, like planets. Note that none of these pieces of hail are disc-shaped. Okay, so to help understand this, I've applied spatial value, and it's something scientists just haven't done. I'm not trying to be an asshole. I'm just saying, to help understand, you have to understand spatial value. You can't quantize space, but you can get a value for it. So matter, which is a charge 0 because it's neutral, has a spatial value of 1, which is Bohr's radius. This is the space in between the electron and the nucleus of an atom. Now, plasma, on the other hand, has a positive 1 charge, because it's hot and charged, and has a spatial value of 0. Meaning there's no space in the star. It's all compressed together. Now, a Bose-Einstein condensate, on the other hand, has a negative 1 charge and a negative 1 spatial value, meaning it's inconsistent. That means it can vary. It can be really, really tiny, or it can be really, really large. So in this aspect prior, you have a negative 1 spatial value and negative charge, because this is a leptonic statical area. And the spatial value is decreasing between the particles. And it's going to have a consistent color charge, which is a spatial value. It's going to be 0 spatial value in stars, and it's going to have a +1 spatial value in matter. Now, stars are made of matter, but it's plasmatic. You might say it's proto-matter. So the spatial value is 0 before it becomes positive 1. And it's negative 1 before it becomes 0. So it's as easy as 1, 2, 3, A, B, C. So in a nutshell, you might say the universe is trying to concentrate. It's very diffuse right here. And then it concentrates all of that energy. And then it becomes telekinetic. I wonder why the universe coincides with the mind so well.